So here we are at the very end of section 6.2, and this is page 19 of section 6.2. And we're going to take a look at one last example. This is kind of putting it all together and solving a differential equation that involves a Heaviside function. Now, up to this point, if I would have shown you Heaviside functions and then said, okay, now let's find the solution for this, we would have been kind of stuck in the water, or we might have had to revert to a piecewise definition of how this differential equation behaves, and we would have had to take a look at two separate equations. But now that we have a way of kind of solving everything in line, we can do this all at once. So we're going to follow the method we did before, and we're going to take the Laplace transform of both sides. So the Laplace transform of dy dt equals the Laplace transform of, I'll put the negative out front, of y plus the Laplace transform of the Heaviside function, switching it to t equals 3. And so I can revert back to my tables to be able to do these, but really the one thing that I just have to remember is that the Laplace transform of a derivative is s times the Laplace transform of y minus whatever the initial condition is. And fortunately for us, we have an initial condition. So in this case, all of this is going to be s times the Laplace transform of y minus y of 0. That's the left-hand side of things. And that's going to be equal to, the other side is just minus the Laplace transform of y. Nothing we can do with that guy for right now. And then it's the Laplace transform of the step function, the unit step function, which we already know is just e to the minus whatever that value is, 3s over s. Right? So you remember the next step is we can plug in our initial condition. We know our initial condition up here, y of 0 equals 2, so that means this thing really is 2. And I'm going to try to manipulate this equation to solve for Laplace transform of y. So I'm going to say s times the Laplace transform of y. I'm going to move this to the other side, plus the Laplace transform of y. I'm going to move my 2 to the other side, equals 2 plus e to the minus 3s over s. The goal of this now is to solve for Laplace transform of y. Remember, our stages are first take the Laplace transform, turn our equation into Laplace land, solve it in Laplace land, and then undo the Laplace, turn it back into functions of t. So on this side, we're going to have Laplace transform of y times the quantity s plus 1. Then over here, it's still the same. Divide both sides by s plus 1. And you basically know the Laplace transform of the solution looks like this. It's going to be 2 over s plus 1 plus this guy, e to the minus 3s over s times s plus 1. So basically at this point we know that the Laplace transform of the actual solution, the particular solution, is this, 100%. So what we need to do is we need to find the y of t that has this Laplace transform. Right? Because if we can find that, we've solved our problem. So a little bit of manipulation goes a long way with this one. And you probably have already noticed this first one is not too terribly difficult to find the inverse Laplace of. So Laplace transform of y equals, I'm going to put the 2 out front, times 1 over s plus 1, and that way it should look pretty familiar as one of the formulas that we have on our Laplace table. And this one I'm going to rewrite in a slightly different way. I'm going to write this one as e to the minus 3s times 1 over s squared plus s. I just multiplied the s through. And by writing it that way, I'm trying to figure out a way to kind of manipulate this a little bit. And so what I really want to do is take the inverse Laplace of both sides. So I'm going to take the inverse Laplace. And when I do that, I'm going to be left with y of t on the left-hand side. The right-hand side is going to be 2 times, hold on, I got dogs coming inside here. So it's going to be 2 times the inverse Laplace of 1 over s plus 1 plus the inverse Laplace of all this stuff, e to the minus 3s times 1 over s squared plus s. Now, s squared plus s, if you're looking at your table, your Laplace table, you are not going to find s squared plus s anywhere. Right? That's not the same thing as this. It's none of these here. I could try to maybe write it as a perfect square, not a perfect square, but a completed square here. The problem is that the top of that fraction over here, the top of that fraction is 1. I don't have an s up top to be able to do those things, right? There's really no way I could do it. It's maybe something like this, but instead, what I can always do is rely on Maple. And we're going to take this fraction right here, and we're going to try to par frac it. And so, via par frac, we should be able to show that 1 over s squared plus s is equal to a couple of things together. So let's see if we can figure that out. Step over here to Maple, and we're going to say convert. We're going to convert 1 over s squared plus s using the par frac, and our variable is s. And Maple says, hey, no problem. That's the same thing as 1 over s minus 1 over s plus 1. So I wrote that down. So now that we switch back over to our notes here, so I just figured out what that thing is equal to as a par frac. And so this thing becomes essentially 2 terms right here, which becomes 2 separate functions. So the next line down is going to be y of t equals 2 times the inverse Laplace of this. So by this point in time, you probably are recognizing that's just an exponential. That's 2 times e to the minus t. The minus 1 comes from down here. Plus, now I'm going to split this up into 2 inverse Laplaces. This is inverse Laplace of e to the minus 3s times the first fraction. Minus, because there's a minus sitting in front of that second fraction, the inverse Laplace of e to the minus 3s times 1 over s plus 1. Now, those two should look pretty familiar. E to the minus something times s times something that we can actually find the Laplace, inverse Laplace of. That's screaming. Both of these are shifted switches, right? So this first one is, let me get my number here, or my marker, 2e to the minus t, plus this guy is going to be the Heaviside function at 3 times whatever that thing is the Laplace transform of. And 1 over s, we're going to use our handy-dandy formula here. That's with n equals 0. So this would be like t to the 0, or just a constant of 1. This is the same thing as u with a little subscript of 3 of t times 1. That's this guy right here. Minus, this guy is going to be the same type of situation, u with a subscript of 3 of t times this. We already know what that's the inverse Laplace of, or what that's the Laplace of. That's e times e to the minus t. So what we have is kind of a great big combination of things. Oh, whoops. Did I do that right? I think I did that right. Oh, no, this shifted. Yeah, upstairs here. This should be e to the minus t minus 3. That's what I should have there. There we go. Sorry, because that shifted. Yep, in the upstairs. So putting this together, we can kind of squeeze it together one more time, and we wind up with 2 times e to the minus t. And this guy right here, this is just u with a subscript 3 times a quantity. 1 minus e to the, I'm just going to make this a little bit easier to read here, negative t plus 3. So how does this thing behave? Well, it behaves like, up until t equals 3, it behaves like 2e to the minus t. So it's going to be exponential decay. And then all of a sudden, when t equals 3, we're going to see this thing turn on, and it's going to be 1 minus e to the negative t plus 3. And sure enough, if you were to graph this thing, you wind up with a graph that looks like that. And we can verify this if we hop onto Maple real quick and just say, hey, Maple, will you plot for us this graph? And so it's going to be 2 times the exponential of negative t plus heaviside t minus 3 times the quantity 1 minus exp to the, what would it be, like 3 minus t, I guess, or negative t plus 3. I'll just write 3 minus t, make it easier on myself. Close parentheses, and let's see, let's make it go from 0 to, I don't know, 5. Oops, t equals 0 to 5. And sure enough, the graph that we have here looks remarkably similar, with a little bit of scale difference, to the graph that we have there on the page. So we can also ask Maple to desolve our differential equation, because Maple actually can handle doing a solution process. So I'm just going to go back in, I'm going to type in my original differential equation and say that equals negative y of t plus my step function, heaviside t minus 3, boop. And then we also have an initial condition of y of 0 was equal to 2. Close my bracket. I actually have to add an initial bracket. And Maple says, yep, I gotcha. And sure enough, that's exactly what we spot when we solve the problem ourselves. So Maple's capable of solving with heaviside in the original differential equation. The problem that we're going to run into in 6.3 is it's not always pretty. So this solution process follows very much the process that we learned in 6.1. First, take the Laplace of the whole equation, solve the thing for Laplace of y, and then invert, take the inverse Laplace in order to get your solution y of t. The hard parts, of course, are the algebra and kind of keeping straight with all the bookkeeping. And of course, you wind up with Optimus Prime. Oh, look at that. Optimus Prime is, what's the definition? Isn't that adorable? Okay, so that gets us to the end of 6.2. Next time in class, we'll practice a little bit more with this and then begin the notes for 6.3. And 6.3 goes pretty quick because there's not a whole lot of new stuff in there.